Now that we understand some of the basics of circuits, let's specifically look at RL circuits, so the resistor inductance circuits. We're going to let E of t be the voltage in the circuit at time t. And in these type of circuits, we have that the voltage is going to be given by EL plus ER. And as reminders, EL is the voltage across the inductor, ER is the voltage across the resistor. Substituting in the formulas that we have for these, in the last video we talked about how EL is given by L times the derivative of I dt, and ER is given by RI. Well, now I'd have a differential equation, and in fact it's linear, so let's start by rewriting it. Moving this to standard form, we have di dt plus R over L times I is equal to E over L. And now we can see that it's linear a lot better. Our integration factor is then given by e to the integral of R over L dt, which is e to the RT over L. Using our formula for solving linear differential equations, we then have that I of t is equal to e to the negative RT over L times the integral of e to the RT over L times e over L dt plus k. In electrical circuits, c has a different meaning, so we're going to use k for our constant of integration. So let's look at an actual example. For this problem, we have an RL circuit with a 1 ohm resistor and a 0.01 Henry inductor. It's driven by a voltage E of t equal to sine 100 t volts. If the initial inductor current is 0, we want to determine the subsequent resistor and inductor voltages, as well as the current. So let's start by organizing this information that we have. Essentially, this problem gives us that the resistance R is 1, the inductance L is 0.01, our function E is sine of 100t, and since the initial inductor current is 0, we have that I of 0 is equal to 0. So now let's set this up based on the thing we just talked about would be the formula for solving this. This gives us that I of t is equal to e to the negative t over 0.01 times the integral of e to the t over 0.01 times sine 100t over 0.01 dt plus k. This is a really hard integral to compute, so we might want to use a computer or integral tables. When we do that, we get e to the negative 100t times 100 times e to the 100t times 100 sine 100t minus 100 cosine 100t all over 20,000 plus k. I missed a parentheses in there. That's okay. We can then simplify this. When we do, we get 1/2 times sine 100t minus cosine 100t, all plus k e to the negative 100t. And we also know an initial condition. We know that I of 0 is equal to 0, so let's stick that in and see what happens. Sine of 0 is 0 and cosine of 0 is 1. E to the 0 is 1, so that gives us 0 is equal to 1/2 times 0 minus 1 plus k. And we can solve that to get k is equal to 1/2. Substituting that in, we now have a formula for the current. So we've done one of the 3 things that we needed to do. The next things we needed to do was find the resistor and inductor voltages. For the resistor voltage, we knew that that was equal to R times I. In this case, R is equal to 1, so we just have that E of R is the same thing as I of t, the thing we just found. We know that EL, our inductor voltage, is given by L times di dt. Using L to be 0.01 and taking the derivative of what we just found to be I, then we can do some basic simplifications, and we get that this is equal to 0.5 times cosine 100t plus sine 100t plus e to the negative 100t.